Hi, everyone. Yeah, you'll need the headphones to hear me. Please raise your hand if you work in the semiconductor industry. Okay, well, good. You're in the right session. I know there could be there are multiple sessions going on. Thanks for coming. Before we get into EDA on cloud, I would like to get to know the audience a little bit more. And please share by raising your hand if you currently run EDA workloads on your premises. Okay. If you have ever experienced a project delay because of limited resources. Okay. If you've ever had to explain to your management why you needed the latest technologies for your project. Okay. Please raise your hand if you plan to migrate to cloud in the next 12 months. Okay. And please raise your hand if you're currently already running your EDA workloads on cloud. Wow, okay. Thank you for sharing that. It looks like we have a very diverse and a very experienced audience here today. I'm Sinem Gülbay. I'm the EC2 Principal Product Manager, focused on compute offerings optimized for electronic design automation workloads, also known as EDA. And I'm thrilled to be joined by a true pioneer in cloud-powered semiconductor design, Jitendra Mohan, the Chief Executive Officer and co-founder of Astera Labs. In this session today, we will dive into the evolving challenges and also the opportunities facing the EDA industry. We'll talk about why some of the leading semiconductor companies are turning to cloud to run their EDA workloads and how you can actually benefit from it by moving your EDA workloads to AWS. And then we'll hear directly from Astera Labs about their silicon innovation journey on AWS. So let's get it started. Let me start sharing some of the evolving challenges that's right now happening in the EDA industry and how we can turn those into big opportunities. Increasing design complexity. The sophisticated and powerful chip designs are driving an increase in the chip design complexity. That's a known fact right now. An advanced EDA infrastructure with the right compute and storage solutions can actually help you to drive those sophisticated designs, unblocking your design needs from an infrastructure point of view. Second challenge the industry faces is time to market. In a highly competitive landscape, a cutting-edge EDA infrastructure can become a competitive edge by streamlining your silicon design, verification, simulations, and that can become a very powerful tool to accelerate your own time to market. Number 3, global teams and enhanced security. Global talent is a huge opportunity if you can tap into it to get diverse expertise and also around the clock productivity. However, it does require an EDA infrastructure that can provide seamless collaboration in a secure way. Fourth, adapting the latest technologies. The rapid pace of innovation in the semiconductor industry can become your direct opportunity to accelerate your own silicon innovation. Adapting the latest hardware and software technologies can help you to accelerate your own innovation by being not bottlenecked by the performance of your EDA infrastructure. And the last part, cost optimization, which is probably a theme across any customer, any industry that we can think of. Specifically, strategically managing your infrastructure to align your investments to your business needs can actually help you to maintain a competitive edge while still delivering very powerful, very innovative solutions and optimizing your spend. Next, I would like to talk about how some of the leading semiconductor companies are leveraging the beauty and the benefit of AWS to turn these challenges into opportunities. Let's talk about some of the key drivers. First, power of scalability and elasticity. In a highly competitive industry with time-to-market pressures and increasing complexity design, scalability is highly critical. If you need more capacity on a self-managed data center, you need to go procure some new data center space, new hardware, new racks, and on top of it, manage it. And unfortunately, none of that happens quickly. In addition, investing in new capacity can be very, very capital intensive. So no one wants to buy more than they need. What that means is that when the projects are starting and scaling up, your demand is increasing. When the projects finish, your demand wanes. However, a static on-premises data center cannot provide the agility to keep up with this varying demand. Let me demonstrate what I mean. This is a typical capacity curve on a self-managed data center. You start a project, you realize you need more capacity. After a certain while, you go and procure more capacity. However, the demand curve is actually not following a similar curve to the capacity curve. The demand actually fluctuates as the projects start and finish. What that means is you're either left with some unused capacity, or as you take on new projects, you're experiencing delays in your projects. And that's simply because the static capacity means that you're always getting it wrong. You either have too much capacity or too less capacity. That's why some of the leading semiconductor companies are turning to AWS. So they don't need to guess anymore. They can just make sure the capacity matches their demand. They can scale up as needed and scale down as needed. Let's take a look at another factor that comes with the scalability, which is the elasticity. What I'm showing here is the daily instance usage from the Graviton 4 development. So this is the prior year. You'll see in the Q3, Q4 timeframe, we had about the daily usage peaking up to 5,000 instances on a day, which is like a typical daily usage during bursting timeframe. And then it was the Graviton 4 I/O tape-out. And you see the demand started peaking up to 7,000 of instances. And later, during the compute die tape-out, it actually peaked up to 10,000. And these are all very big instances. What I mean here is these are several 100,000 of cores. Now imagine the power of being able to scale to 100,000 of cores and just scaling down when you don't need it. This helped Annapurna, who is part of the AWS Amazon team, who is the designer behind our Graviton 4 silicon. This allowed them to really free themselves from all the scalability issues and gave them the scale when they needed so that they could accelerate their designs without the additional CapEx spend that would come if they needed to invest in a capacity for their peak usage. The power of scalability and elasticity is so critical to accelerate your innovation and also optimize your spend. The second big driver of why we see some of the semiconductor companies are choosing AWS to run their EDA workloads is the global presence and enhanced security. We talked about the opportunity that comes from a global presence, being able to tap into that diverse set of pool. But it does require an infrastructure. And AWS provides a robust, highly secure, and global infrastructure that can help you to connect your teams globally in a highly secure way so that they can all access to the same data, same tools, and work real time. That's so powerful. When you need to expand into a new region to access to that talent, bringing compute or storage closer to that area, that region, is so powerful. Let's see how some of the customers are actually seeing the value of this. TSMC, the global leader in semiconductor manufacturing, has certified Siemens EDA tools on AWS for N2, N3 process node technology. This is very powerful. This move means that designers all around the world can now accelerate their own design, leveraging the advanced manufacturing tools from TSMC, the powerful tools from Siemens EDA, and running that on a very robust, secure, and global infrastructure. This move will help designers to accelerate their design in a very flexible and efficient way. Let's hear from another customer, Marvell. Marvell, a leading semiconductor company in data infrastructure technology, has collaborated with AWS to drive their cloud-first silicon design. This collaboration provided Marvell global scalability wherever they needed, all around the world, robust security with AWS's highest bar on security, and potential to enhance their operational efficiency, which is very, very critical in an industry like this to maintain your competitive edge. In their words, this is helping them to accelerate their chip designs, which is so important to meet the varying customer demands in this industry which has very, very rapidly changing needs. Let's talk about the last but not least benefit, the key driver of running EDA on AWS, and that's selection. AWS provides the latest hardware and software innovations, latest technologies, so that you can take advantage of them to accelerate your own innovation. Selection is highly, highly important for two reasons. One, accessing to the latest technology means that you are actually optimizing your EDA license costs, which is probably one of the biggest spends that you have currently. Two, it's so important so that you can actually use the right compute solution for your workload needs. And you don't try to make one thing fit to all different needs. Let me explain what I mean. Let's start with an example of what does it mean to have just 1 quarter of delay in accessing to the latest technology. Here, we will assume that with each generation, you are adding more performance and reducing your compute needs by 20%. What that means is, let's say this year, you were going to go and invest in 10,000 generation N chips, but with the latest technology, with Gen N plus 1, you can actually get 8,000 chips. So you are saving 20%. We'll also assume that with each generation, between Gen N and Gen N plus 1, there is a 50 watt of power savings per chip. We'll assume the CapEx is $10,000 per chip, and it's same for Gen N and Gen N plus 1. So it would be the same investment to invest in either generation. And let's assume that on your premises, you use a 6-year lifetime per chip. Now let's take a look at what will it cost you to just have 1 quarter of delay. Again, 1 quarter, 3 months. Well, first, instead of procuring 2,000 of the latest chips, you needed 2,500. You needed 500 more chips because you're not taking the performance benefits that comes with the latest generation. That means an additional 125 kilowatts of capacity in your data center. That also means $5 million more in CapEx. And over the lifetime, you are going to be looking at 7 gigawatt hour of additional power use. Think about it. This is just a 1 quarter delay impact. If you think about accessing to the latest technology as soon as it's available and not worrying about having it on time, the impact is huge. So we talked about why it's so important to access to the latest technology, but one more thing I want to talk about is why choice matters. What I'm showing here is a typical EDA workflow. The different workloads of front end and back end, as we refer them. What you see here is that one size fits all does not work for EDA. A front-end design workload, such as design verification, has very different compute and memory needs than a workload like the physical verification. Trying to make one solution fit all means that you're either not utilizing your resources efficiently, or you're not delivering the enough performance your workloads needs. In addition, projects evolve, tools evolve. Your optimal CPU to memory ratio might actually change over time. But you make a hardware decision at the beginning, right? And no one likes to get rid of a hardware before its useful lifetime. So what happens is you end up putting some of your workloads on older hardware or on hardware that doesn't have the optimal CPU to memory settings for that workload. What does that mean? It means that you're actually not maximizing the return of your EDA licenses. When ideally, what you want to optimize for is getting the maximum use of those EDA licenses. Speaking of choice, I would like to share one customer anecdote here. So NXP, a leading semiconductor company in secure connectivity solutions for embedded applications, has selected AWS to drive their next generation semiconductor innovation. And I would like to share the benefit they saw in their words. They said that leveraging AWS's portfolio of cloud services has been instrumental in accelerating their semiconductor innovation development and production cycles. By leveraging the broad choice of compute offerings AWS provides, NXP has been able to really optimize the compute needs based on their workload needs, not only optimizing for performance, but also optimizing for price performance. So let's talk about some of the broad choices that are available for EDA workloads. When we look at our instances, compute offerings that are optimized for EDA, you'll see a wide selection across different processor options, such as Intel, AMD, AWS. And I would like to take a few minutes to take us through the latest EC2 offerings. Intel-based instances, powered by custom Intel Sapphire Rapids CPUs that are only available on AWS. By investing in a custom Sapphire Rapids design, by collaborating with Intel, we were able to deliver up to 20% higher performance versus the previous generation Ice Lake-based Gen 6-based instances. Also available as an option, a high-frequency version with up to 3.9 gigahertz of sustained all-core turbo frequency. These two instances, R7i and R7iZ, which come in 1:8 vCPU to memory ratio. So for each vCPU, you have 8 gigs of memory, is an ideal fit for the workloads that really look for great performance and great memory. AMD-based instances, powered by AMD Genoa CPUs, offering up to 50% higher performance versus the previous generation Milan-based Gen 6 instances. These instances, again, come in a 1:8 vCPU to memory ratio, a great fit for your workloads that are demanding very high performance and also looking for memory that is up to 1.5 terabytes. And our AWS Graviton instances, powered by Graviton 4 CPUs. The latest generation Graviton 4 CPUs offer 30% higher performance versus the previous Graviton 3-based instances. These also provide the lowest cost per gigabyte across all the Amazon EC2 instances. We also have an X variant in this family, meaning for each vCPU, you get 16 gigabytes of memory, scaling up to 3 terabytes. As we spoke about different workloads needing different needs, we do realize that some workloads will need up to 3 terabytes of memory or higher core-to-memory ratio. And that's why we see this is such an important area for us to make sure we are delivering you enough choices so that you can actually optimize your compute selections for your workload needs. Let's talk about Graviton for a second. When we look at the tool availability across Graviton-based instances, the trend that we see is that it's rapidly changing. The slide we had probably only 6 months ago looked very different than this slide. And the slide we will be showing in 6 months from now will look very different from this slide. By end of 2025, we expect majority of the tools will be supported on Graviton-based instances. Why this is important? This is important because it's giving you a choice. It's giving you a choice to optimize for different workload needs, whether that might be a different performance, price performance, or cost profile. Having choices arms you with the selection so that you can really optimize for your needs. Synopsys, a leader in providing EDA tools for the semiconductor industry. We recently collaborated with Synopsys to make sure that our mutual customers can actually get the highest performance available. Through this collaboration, we looked at how can we deliver the highest performance we can, enabling these tools to achieve even better outcomes. As part of that collaboration, AWS team has tested Synopsys PrimeTime on ARM-based AWS Graviton 4 instances. I'm sure most of you here use PrimeTime. And let's see what we have observed in our own testing, in our own benchmarking, running PrimeTime on Graviton 4. The early engineering builds using Synopsys PrimeTime on Graviton 4-based instances, R8G, are performing similarly to R7i with half the number of vCPUs. Again, very similar performance with half the number of vCPUs. Talking about performance optimization, talking about cost optimization, having more tools means that you can actually optimize your spend and accelerate your own innovation. The broadest selection that we deliver help teams like Annapurna to optimize their own spend while driving innovation at the fastest pace. Which brings me to our own journey. Amazon's own silicon journey started a decade ago when Amazon acquired Annapurna Labs back in 2014. Today, Annapurna Labs designs all AWS custom processors, from Nitro to Graviton to machine learning chips such as Inferentia and Trainium. Over the last 10 years, there has been an exponential increase in the chip complexity. Yet the delivery speed kept increasing and increasing. Over 10 years, 6 generations of Nitro, 4 generations of Graviton, and 3 generations of machine learning chips. This is such an incredible pace of innovation. So let's pause here and let's ask, what has really enabled this? What has enabled this type of pace of innovation for Annapurna Labs? Well, it really goes back to Annapurna's own digital transformation journey. When Amazon acquired Annapurna Labs were running all their workloads on premises. Over time, they first adopted the hybrid approach, where they still kept their own self-managed data centers, but started running some of the applications on AWS. Today, the only thing Annapurna team is running outside of AWS is emulators. What does that mean? It meant that they really freed themselves from any constraints on scale. They were able to scale up when they needed with the power of AWS's robust, global, and secure infrastructure. And they were also be able to do that without a huge CapEx spend. The scalability, elasticity of cloud, giving them choices for different needs, allow them to really innovate at a great speed. So with that, I want to hand it off to Jitendra to tell about Astera Labs' own silicon innovation journey on AWS. Please give a hand for Jitendra.
All right, Sinem, thank you very much. If I can summarize my presentation in 3 words, they would be what she said. So I would like to give you a perspective of somebody who's been the end user of all of the services and instances and such that Sinem just talked about, and hopefully share some insights before the urge to go to the slot machines really kicks in. My name is Jitendra Mohan. I'm one of the co-founders of Astera Labs. My background is actually analog circuit design with zero training in IT. I did moonlight as our company's IT engineer when we were small, and our official IT team, some who are here, are still paying for my sins. Fortunately, I'm also the CEO, so I can get away with it sometimes. Let me tell you a little bit about Astera Labs, and then we will kind of jump into, so that you get an idea of the scale that we run in at AWS, and then we'll jump into the EDA and the IT infrastructure. So we are about a 7-year-old company. We have more than 400 folks in the company worldwide. We now have 4 product lines that we are released out into the industry and generating revenue. Based on our last quarter, we are at a $400 million plus run rate in revenue. We have several design wins. We have shipped over 10 million devices. And importantly, we ship to all of the major hyperscalers and AI platform providers. So they're very, very important clients for us. So we use AWS services, but we also sell into the hyperscaler industry. This slide here kind of shows our journey over the last 7 years. We are incorporated in October of 2017 in a garage. And over the next several years, we've picked up a few awards. Several financing rounds later, we IPO'd in March of this year. So couple of actually important awards are missing in here in 2019. I just noticed when I was preparing for this talk. I'll touch upon them later. But just very importantly and very satisfying for me personally, coming from a design background, is the number of tape outs and chips that we have released over the last 5.5, 6 years. As Sinem mentioned, the pace of innovation has really picked up. And I counted, we've done more than a dozen tape outs over the last 5.5, 6 years, all 100% on AWS. That is a little bit maybe unique about what we did. How we were able to do that. And this is a slide that is really close to my heart. We presented to our customers and our partners as well. Kind of 3 pillars on what has made us successful. First is our execution excellence. We've gone literally from PowerPoint, meaning an idea, to samples in customers' hands in less than 1 year for multiple product lines. We've been able to do that through a lot of partnership, very, very close partnership that we have with Synopsys, who are our primary EDA tool vendor, with TSMC, which manufactures all of our chips, and of course with AWS, which is where we run all of our EDA infrastructure. And that has just allowed us the level of flexibility that I'll describe with some data in the coming slides to deliver that excellent execution that we are known for. Okay, so let's go back to the beginning, as they say. Back when I was the IT person, 3 people in the company, getting started, I think it was April of 2018, we had a choice to make, which was either go on-prem, which was actually the most popular advice that we received. Buy a rack, put a few servers in there, and you will get started. Or go hybrid, which is what many of the other companies were doing at the time, a little bit on-prem, a little bit on the cloud. Or another option we considered was to be 100% in the cloud. And our decision-making maybe was not the most sophisticated, but this is how we ended up being 100% on cloud. Number one, we said, none of us knew IT. Managing all this infrastructure is going to be painful. If you are hybrid, it's double the pain. You have to manage your on-prem, and you have to manage the cloud. So that was an easy rule out. We did not really have the resources or the knowledge to put together our own on-prem. And so with a bias for action, we decided to just go on the cloud. In hindsight, a lot of the people who shared this advice with us did not tell us how difficult it would be, almost foolish. But in typical startup fashion, we said, this is where we are going. And we overcame whatever obstacles came our way to deliver the results that you saw in the last couple of slides. So let's look at how we do this. It's probably hard to read this chart on the right-hand side. It's even more difficult to understand, especially for somebody without any IT training. But the fact is, we were able to put together our EDA IT infrastructure, all based on AWS cloud, AWS services. And it was all designed by the AWS ProServe team using all of the different AWS services. We run our fixed workloads on reserved instances, which is no surprise. We use our compute on, on demand and spot instances. We actually, we were talking earlier before the session about storage. Storage is very, very important for EDA workloads. And we, at the time FSx was not available, we decided to spin up our own NFS server using EBS volumes. And that thing would crash. You would just know in a company of 12 people, 10 engineers, if everybody just stood up and you could see everybody stand up, you knew the file server crashed. Fortunately for us, FSx was introduced. Actually, AWS helped us debug all of that. FSx was introduced. We migrated all to FSx. And so now our combination is EC2 instances, largely Intel, some AMD, and some Gravitons running all on FSx. And then we recently started using AWS backup for that as well. So this chart here is probably my most important contribution to this talk. What you see here on the bottom is our spend. The axes have been removed to protect the innocent. But if you were to try to fit an exponential to this curve, you would come pretty close. And this is also what gives a little bit of a heart attack to our finance team. Our IT teams will find it very difficult to justify this, to others in the management. So before I jump into here too much, maybe I'll do my own little poll, which is how many of you are actually designers or actually use these services to design chips, etc.? Okay, very good. So I think this might appeal to you a little bit more. And when I look at this chart with an IT mindset, I'm also like, what's going on? This is bankrupt us. But then when I put on the sort of the designer or the CEO hat, this gets us into perspective. Because when you're trying to deliver a solution to your customers, the biggest cost is not IT. As Sinem mentioned, the biggest cost is actually time. If you lose time, no amount of money or resources are going to be able to make up for that time. The second largest cost is our engineers, resources. The third one is manufacturing, and specifically masks. If you are in these advanced processes, such as the one that we use at TSMC, a mistake will cost you millions of dollars. And so this is where really the power of cloud comes in, because what we can do with cloud and what we have done with AWS is to really accelerate our time to tape out, increase the productivity of our engineers, and really make sure that the chip that we are taping out is of high quality. And what we've been able to do is really improve the amount of simulations and such that our engineers run by a factor of 10 easily. Before Astera, I was at a large company. I was at Texas Instruments. We had access to a compute farm. And I think you asked the question, how many of you thought it was enough? We never thought our compute farm was enough. So when we got into AWS, and this idea of having infinite compute was so attractive, and we'll talk about a little bit more on how we actually were able to do that. But bottom line is our engineers were running 10 times the simulations that they would have run otherwise. And that directly contributed to not only shrinking the amount of time it took to design the chip, but also improve the quality of the chip. And that's what we call front-end design. This is where you're designing, simulating, finding bugs, fixing them. Then you move from there to an implementation phase, where you're now translating these design into polygons that you will eventually send for manufacturing. And that also becomes very, very interesting. If you have a fixed installation, then you have to decide, once you start into this implementation phase, am I going to use my infrastructure for implementation tools, or can I continue to run simulations? Well, we didn't have to make that choice. Our engineers continue to run simulations even after releasing the design for the implementation phase. And now what happens is, as you keep running simulations, even after releasing it to implementation, at some point you will find an issue. And now what do? Well, what our implementation team did, they continued to run on the infrastructure they had for the primary path. But then they would start a parallel path and saying, OK, let me take the change that you're giving me. Maybe it's a bug fix, or maybe it's a new feature. And I'll start a parallel run, which is now behind the main one. But if it is able to catch up, then it becomes primary, and you just drop the main one. And so the ability to do so many things in parallel greatly positively impacted us in terms of allowing our engineers to be more productive, taping out faster, getting silicon in the hands of our customers faster, and that eventually led to the success that we have enjoyed this far. So with that, let me go a little bit into the details. And this is the similar charts to what Sinem was showing about how we use our AWS infrastructure. The one that's my favorite is actually the one on the top right. And this shows how we have used different instance types. And if I could, this goes over a period of about 2 years. But if I could extend it even before, you would see that prior to this, we used yet different instances. We actually started with C5 instances, went to M5 instances, and then R5 became our workhorse because of the memory requirements. As soon as R6 came about, we started moving our workloads to R6. As soon as R7 came about, we moved to R7, and you will see that. And we heard about R8s today, and I'm sure if I get the opportunity to present again, there will be R8s on this slide. Not only that, if you look at this kind of the lighter color, the X family that Sinem mentioned, X2s, and especially the blazing fast X2s, and before that Z1Ds, are also two instances that we use for the really long-running simulations that are really critical. They always happen towards the end of the tape-out process. We call them gate-level simulations. And so we are able to utilize just the fastest machine possible to run those simulations. And not only that, what our engineers will do is they will, for every simulation that you need to run, they will start 3. One that runs at the maximum speed, doesn't store any data. At the end, you get pass-fail. If you passed, life is good, you can kill the other 2 jobs. If there is a mistake that happens, then the job right behind is coming up with more information that you can use to debug what happened. And the job right behind, I have to be careful not to fall off the stage. The job right behind has all the data, all the waveforms, everything is saved. So again, an example where we structure our workflow to make full use of the scale and the elasticity that the cloud brings. What you see here on the top left is our storage. In green is the NFS file server that we kind of spun up ourselves, and it maxed out at 160 terabyte. But over the course of 2 years, we went from 160 terabytes to 600 plus terabytes, all SSD, which would have been hard to do. Now, what this chart doesn't tell you, it looks nice and linear, but the way storage goes is when you are, hiking on a weekend on a mountain, you will get a call, sometimes from our team here, that storage is now at 90%. So by the time you come back, you're able to punch in a few keys and relieve that pressure right there and then. And over time, you go ask the engineers to clean up, which they are usually very reluctant to do. But nonetheless, you manage that. Over the time, the amount of storage just keeps on increasing. But we don't have to ever worry about jobs crashing or running out of storage at the last minute. All of this comes at a cost. And what we have done is to manage our costs by judicious use of spot and on-demand. So what you see, the 2 charts on the bottom right, on the right you see our instance hours that we use, our usage in hours. And you can see they're dominated by spot. On the left-hand side, what you see is the cost. And even at that level of usage, it is still dominated by on-demand. And in the next couple of slides, I'll touch about how we manage to modify our workloads to make better use of spot instances. Now, all of this compute is excellent, but it's of no use if you don't have enough licenses. So this is where EDA and IT come together. Back in 2018, we worked very closely with Synopsys to say, hey, we are on the cloud. If necessary, we can deploy all of these machines, but you only gave us 100 licenses. It doesn't help. And to this date, I don't know what they saw in us or why they did it for a team of 12 engineers with no product. But they allowed us to have a kind of a per hour, or I forgot, maybe it was a per minute or a per second usage model. It was private for us at the time. Since then, it has been released to the public. And now we use their cloud portal with what they call a pay-per-use model. And what you see here is our daily usage, very similar to the chart that Sinem showed, where you can see there are periods of spikes here, which are 10x. I don't know if you noticed that in the previous chart as well. There is almost a factor of 10x change that happens during a project cycle. And with this, again, we just free our engineers to run whatever type of simulations that they want to run, the number of simulations that they need to run to ensure the highest quality tape-out. And so this goes extremely hand in hand with the scalability of the cloud. Now about using spot machines. So we understood early on that if we do use infinite compute with infinite licenses, we'll go bankrupt very rapidly. So we decided to focus on enabling a workflow that uses spot. And what we did here is we created a workflow where you start the simulation on a machine, and we used VCS from Synopsys to do that, on spot instances. But we used the capability of save restore, which was built into VCS. So we set it up in such a way that when we get a notification from AWS services that says, hey, the spot machine might get taken away, we save the state of the simulator. The job then crashes, dies because the spot machine died, but then the job scheduler will automatically restart it from the saved point. There was a little bit more detail that went in to make sure that the save actually happened and the restore happened automatically, et cetera. But as a result of this, we were able to keep our workloads on spot machines for a large percentage. And this was extremely, extremely helpful. And we use this capability to date. Now, if you move towards the back end, so we also run all of our backend on AWS Cloud. The backend characteristics, the job characteristics of backend tools is very different. They are typically looking for much larger machines, much bigger footprints, and all of those requirements are fully fulfilled by the variety of instances that are available on AWS Cloud. And so we run everything from synthesis, place and route, timing analysis, DRC, all of it is done on the cloud. And it has been very powerful for some of the reasons that I mentioned before, where we can have parallel flows going with AWS. We can include last-minute features. We can include last-minute bug fixes, and in general have a higher quality of tape-out. Here is another example. So with the success of the cloud model for front-end VCS tools, we again requested our EDA partner, Synopsys in this case, to enable the same thing for backend, which they did for Primetime and ICV. ICV is a tool that is used at the very end of the process. When everything else is done and you're trying to remove all of the design rule violations in your design, it's a process that can be parallelized a lot. So again, we put the elasticity and the scale of cloud to bear here, where we can run multiple machines. Multiple engineers can be working in parallel on the same design to take care of all of these DRCs. And again, you can see easily a 10x or more dynamic range in the amount of ICV usage. That coupled with the fact that you have the fastest machines available, that you can split the workload over, again gave us the scale and the speed that we needed to accomplish these rather complicated tape-outs. So I think the main takeaway here is cloud model, whether it's for front-end design or back-end design, has resulted in shrinking time to market for us, shrinking time to tape out, more efficiency from our engineers. And just to summarize, access to virtually unlimited resources, at least at the scale that we are operating at, much improved chip design process. The fact that not only can you tape out sooner, but you can tape out with much higher quality, that is just unachievable otherwise. And at the end of the day, it gets our chips in the hands of our customers sooner. And that's what matters. Right, with that, let me call Sinem back on the stage.
Okay. To close, I just wanted to look at together the future of EDA. As we look to the future, I think the one thing that's very clear is that cloud-powered EDA will continue to accelerate. And at AWS, we are committed to be at the forefront of this revolution. We'll continue to invest in the latest hardware and software solution. We will collaborate with our EDA community, and we'll continue to provide the robust, secure global infrastructure for you to accelerate your own EDA innovation. So I encourage you all to connect with us, to connect with the experts here, and explore the potential of bringing your EDA workloads to AWS and becoming part of this journey. Thank you all so much for joining us today. Thank you all so much for your time. I'll ask 2 more minutes of your time. Please fill the surveys for us That means the world to us. We take a look at all the comments in those surveys, and it also helps us to understand what type of content we should be bringing next year to you. So I really appreciate if you can take a couple minutes to fill the survey. We've left our contact information. Those QR codes will take you directly to our LinkedIn pages. Feel free to connect to us. We would love to get your ideas and see in what ways we can collaborate together. I want to thank you so much for your time,
Thank you.
and thank you all.
My
Thanks to
pleasure.
Tendra.